All right, everybody, let's get ready for the final course of the SGP Graduate School. I'd like to give a little bit more of an introduction to Markus over here, because some of you may not be familiar with him yet. So I did my PhD in Delft, and there we had a group that had a lot of different topics that were going on. So we had computer graphics, offline, online rendering, geometry processing, visualization. And one of the things I really enjoyed is coming from this sort of more geometry processing, seeing all these different topics and then learning from that and seeing how can I integrate that. And when we were designing the program for this course, we thought about what can we do, and one of those things was maybe integrating some of that from outside of classical geometry processing, but I think it's very related. So Mark's going to talk about acceleration structures and bounding volume hierarchies, and these things show up in a lot of tasks that we have to do on a daily basis. So for Nathan's talk, these closest point queries, that's where we have to use these bounding volume hierarchies. Maybe you want to do Monte Carlo geometry processing, that's where you'll need this. So I'm very excited for this talk, and Markus, take it away.
Yeah. Let's see if this still... Yeah, okay, good. Awesome. Thank you for the introduction. I'm glad you didn't cover too much of what I'm going to say here on my introductory slide. But yeah, as Ruben mentioned, I'm coming from a slightly different direction. So my main focus is on real-time rendering. And I'm specifically interested in data structures and algorithms that make things more efficient. So I tend to work on a quite foundational level on stuff that ends up at the bottom of a rendering engine that kind of drives that kind of stuff. I'm currently in Leeds, although originally from Switzerland. So if you all want to switch over to Swiss German, I'll see if I can make up all the necessary words that I've never said in German before. But yeah. One thing that I also want to include a little bit in today's talk is kind of this idea that algorithms and data structures go hand in hand with hardware. So one of my kind of core ideas is if you design a method, you have to kind of pick algorithms and data structures with your target hardware in mind. So that's something I'll try to mention occasionally. It's the kind of thing that makes a difference between something that works reasonably well, maybe even solves your problem a bit, but then you can still go a factor 2 or 10 times faster by just being aware of some choices that you can make. Normally, whenever I start in a new place, I ask this question, whether or not anybody is surprised about the topic being presented. I hope everybody here agrees that we are going to talk about bounding volume hierarchies, and you're not expecting an exam or something. I saw there was stuff going on. If anybody's surprised, put up your hand now. Okay, no, that looks good. It is my first SGP. I want to figure out a little bit who's here. So I have a few questions I would like to ask you guys. I'll start with an easy one. Who here plays computer games? And, oh yeah, people put up their hands, cool. Normally, I have to lower my expectations a bit, students don't really want to do stuff, so you can also just nod or shake your head. It's a little bit less effort. Quite a few. Follow-up question. Ray tracing on or ray tracing off? On, okay, yeah, cool. Well, that aside, a little bit more about the background. So how many here come from a computer science-ish background, so bachelor's or master's? That's a lot of hands. Any pure mathematician people? There's still a few hands, nice. Anything else? Cool. What have you been doing before? Okay, cool. So I originally came from engineering physics and did my PhD in graphics, so it's cool to see a little bit of other stuff I represent here as well. Maybe a springing question. Real-time rendering, we work with C++. So how many here are C or C++? That's also good. I had originally a lot of code on my slides, but I've started removing it a little bit and getting rid of it. Not sure what to expect. The follow-up question, if there hadn't been that many hands, is how many of you work in compiled languages? So something like SIG or Odin. Rust programmers can also raise their hand, although it's not as hip anymore. Yeah, okay, cool. How many are pure Python or MATLAB? Okay, cool. How many of you do GPU programming? A little bit more than just libraries like CUDA, shaders. I'll try to mention some stuff around this as well. Now that I kind of like spring a question for my talk, how many of you have already used BVHs exhaustively? Ooh, tough crowd. Okay, we'll see. I hope I can give you something useful out of this anyway. Also, one thing, like if you have questions, just put up your hand, wave a bit, and we'll take it immediately. No need to wait to the end, although I mean, you can ask stuff in the end as well. I'll start with something simple. So I'll say the phrase BVH, or bounding volume hierarchy, quite a lot. BVH means bounding volume hierarchy. Just to make sure we're all on the same page, I'll show you some illustrations. This is just, I searched for it on Google and took the first few hits that were served to me. This is from Wikipedia. They definitely had a creative choice for their objects, but hey, it's a bounding volume hierarchy. I got served something from NVIDIA. This is by, well, a series of articles by Tero Karas, one of the people who has been doing a lot of research into this kind of stuff in ray tracing. So this is kind of nice. They switched to a little bit more of a, like, for us, classical object, triangles. The physically based rendering book also popped up. They also have an illustration, this one. And they have a chapter on bounding volume hierarchies. So, well, yeah. If you look at the course homepage, you see this beautiful teaser that I put together. Yeah. Questions. So some early observations about this. I mean, I have something specific in mind, but I'd like to hear what you guys like think here. What's like common here? Any observations? Hmm? Yep. You said something specific there that I want to kind of go into, or that was what I want to highlight. You also want to say something, or? Yeah, I'll actually go and tell you that's not necessary later, but let's not spoil too much. But yeah, the main thing I want to highlight here is that for some reason we've always drawn these rectangles that are axis aligned. So one of the most common choices for the bounding volume in the hierarchy is an axis-aligned bounding box, AABB. It's another word I'll say quite a few times. For the people who are listening to this in a recording, I don't recommend turning this into a drinking game. Might not make it towards the end. It's not necessary to use this specific shape, although it's very common. If you don't have a specific reason to use something else, it's probably what you should stick with, and it's what I'll show mainly here. It kind of provides a nice trade-off between simplicity and how well it encloses stuff. Although there have been recently some papers at, I think, Eurographics, where they've kind of tried to move away a little bit from it and started using OBBs, so oriented bounding boxes. So they tend to match the objects a little bit better, but they're a little bit more complex. I have a few motivational slides around this as well. I'm coming from the graphic side of things, and I would go as far as saying that if you want to do ray tracing, you need some sort of acceleration structure, and the bounding volume hierarchy is what you will go for these days. If you have any sort of non-trivial problem, you probably can't ray trace it without anything at all. You've probably also all heard of hardware ray tracing, so RTX, and I mean, what enables us to do real-time ray tracing these days is really this combination of having the bounding, like having all of this knowledge about bounding volume hierarchies, being able to construct them and traverse them efficiently, but also then designing them hand in hand with the hardware. So somebody once mentioned that like what enabled us to do this a few years ago, or like NVIDIA, is really the combination of 50-50, like advances in hardware, but also advances in like the methods themselves. I have one example here. This is a test scene compiled by one of my PhD students, Thomas. He is looking at foliage a lot. That's why you see a lot of trees. This test scene has 5.7 billion instance triangles, so the total number of triangles that you can see in this scene is somewhere around 5.5 billion. Yet this is really easy to ray trace in real time these days. Like, you just construct your BVHs in your favorite API, you throw your ray tracer at it. I mean, this is fairly simple rendering. It just does a primary ray and a shadow ray. But outside of ray tracing, if you were doing normal rasterization, this would be really difficult to do. This is really too much data to chug through. So you would have to do some sort of optimizations, and you would probably end up using something similar as a BVH for this as well. Now, I don't want to talk just about rendering. You will find these things in other places as well. Although my first example isn't, again, rendering, culling, determining if objects are visible or not. They're used in collision detection, so you might build hierarchies over your meshes, over your triangles, and then do a dual traversal to find where they intersect. In simulation, where you have a lot of points that move around in order to get an idea of where they are. And in general, any sort of like spatial query, like a simple example is, hey, I want to find all of the things that are within a radius R of P. Geographic queries are also an example of this, where you maybe have a map, you have a point, and you want to find things around this. Although those people tend to work in quite weird and strange spaces. Now, aside from like ray tracing, I've also used this quite a lot. So cluster shading, which is one of, I would claim, standard techniques these days. We're looking at how to manage lots of light sources, and in 2012 we were able to show that you can actually do tens of thousands, maybe hundreds of thousands, maybe even more lights. And one part of this relies on a BVH, where we find like light sources that affect a certain point efficiently. So it's some sort of range query. In Delft, I work with a colleague on Mark on TSNE, which is a way of visualizing high-dimensional data in a low-dimensional embedding. And there we also use the BVH to figure out neighborhoods of points. One of my current main topics in research is compressed voxels. While we don't really use BVHs directly, we have a very close related data structure, an octree, where we don't actually use it for acceleration, but for compression instead. So that's another thing you can sometimes do with this. And I mentioned this a little bit during the introduction. This is a little bit my soapbox, like my research pitch, in a sense, so take it with a bit of salt. But I mean, we're sort of reaching the limits of hardware. Like 15, 20 years ago, you would get double the performance 2 years later, twice as much memory, whatever. The joke for 26 is definitely the other way around. Like, you might get half the memory in a few months from now. So in order to do more, in order to be able to scale our methods further, we need to work on more efficient methods on the software side, both like computationally and in terms of memory storage. And this is something where I believe structures like the BVH really are kind of a core building stone, at least related to graphics, and maybe also, well, hopefully, some people will say that, hey, this is useful for me as well. A bit more on the goals here. So when I was invited to Ruben, sent me an email. He mentioned a little bit what he said, like, hey, this is not a topic that comes up very often around here. Can you kind of reintroduce this and remind people that these things exist? So that's one of my goals. I will give you some starting points. That if you go out and research and read about papers, you kind of have the context where to place these different techniques. And I want to talk a little bit about like some considerations, specifically when you kind of like then go on to construct this in practice. What to think about, like where you can easily gain this extra like 2x or sometimes 10x speed up by just making the right choices in the beginning. This includes kind of a practical, quick, like you're sitting in your office Thursday afternoon and you need a BVH by, well, end of week. What do you do? Example, basically my go-to choice for building something and then kind of seeing how to scale it differently. Normally, I would now just give you a detailed plan. Before that, I want to give you a bit of context. And to do this, I ask you all to imagine that you're teleporting back to your first algorithms class. Audience feedback, you may let out a collective groan on this idea. That's fine. Here, let's just start with a very basic problem. We have a list of n values, and we want to check if it contains a certain element. Then, well, either say, hey, it's here, it's somewhere, or not find it. Simple example. Most simple solution to this is, well, yeah, we just check each value in turn until we either find the value or reach the end of the list, in which case it didn't exist. Not super interesting, I hope. Most people have seen this before. This would be ON. Yeah, worst case, we have to check all the elements. Otherwise, we check on average half of them. Interesting thing might be that this is quite hardware friendly. So all of our things that we've come to expect from modern computers, like caching, it works well. Prefetching, we can probably rely on getting the right thing for us. And this is relatively easy to parallelize or SIMD if you want to. Yeah. But yeah, you still have to check each element. Quickly moving on. Likely the next thing you would hear in such a class is maybe binary search. So if we have a sorted list and want to do the same thing, we don't have to check all elements. We can do this clever thing where we start somewhere in the middle, check whether or not we should consider the bottom or top half, and then basically do the standard divide and conquer approach and so on until we find our element. And I mean, this is the classic example for something that's log n. If you have 1 million elements, you do 20 checks. So that's nice. But it's also worth considering that maybe this is not as hardware friendly anymore. We're now jumping around in memory a lot, so our caching doesn't work. Our prefetching system probably doesn't know where to go look next, so we might stall a lot more. But for large lists, this is probably still worth it. If you look at this, however, it kind of requires a sorted list. Now, one observation I've made in my career is that data never arrives in the shape you want it. So we probably have to take our data, sort it in order to be able to do this. And this is not free. Typical sort would be n log n. Or if you like radix sort, kn. Although we can hand wave a little bit and say that probably the key size is similar in size to the log n of the elements. So if you have 4 billion elements, you would have probably a key that's around 32 bits, et cetera, et cetera. That changes our analysis a little bit. So if you have random data and want to use this, we have to sort first. So that changes our cost of doing this to n log n plus then log n for the search. And that turns out to be then no longer worth it compared to just a single sweep, like the iterative version. So something more that we have to think about when doing this kind of stuff. And I'll now change the problem a little bit, maybe a bit more of a representative case. So now we still have a list of n values, but instead of looking for one specific element, we now look for multiple elements, so Q queries. I would say that's fairly common. This is also, actually, who has seen this code review by Mike Acton before? Cool. I like pulling it up. I really like the style with the poses and so on. But one common observation is that whenever we do this kind of stuff, we seldom have one object and one query. We probably have a lot of objects and lots of queries, like ray tracing. You have millions of rays. Collision detection, you have millions of triangles and so on. Now, if you have many queries, it changes things a little bit. Our simple thing becomes, simplest way is just repeating the search multiple times, so we get a complex of QN. If you do the binary search, well, the first part, sorting our list, it's unchanged. It doesn't depend on the query, so this stays n log n. But our second part now becomes Q times log n, where we repeat this binary search Q times. And that then becomes worth it, at least if our number of queries is large enough. So with this, I want to quickly summarize two first observations. And one is that whenever we do this kind of stuff, we need to organize our data first, like assets. You don't get a nice BVH served to you, you have to build it somehow. And this becomes especially difficult or problematic if you have dynamic data. And the second observation is that your number of queries that you make against this data will matter a lot. It might not be worth it if you have very few queries that you want to compute. Yeah. There is also one slight tangent that I want to go on. Here it's relatively easy to spot, but we have two lists of the kind of same thing here. It's just integers in this example. We could, in fact, turn this upside down and say, hey, we're going to sort the other list and take our first list and check it against it. And that's something to keep in mind when you're trying to do this, that sometimes it's worth flipping this on the head. There are examples of this in ray tracing. So normally when you ray trace, you build your hierarchy over your triangles, you throw rays at it and see if you find intersection. You can also build a hierarchy over your rays and then take the triangles and traverse it against the rays. People have tried this, it works. It's less common because it has a few downsides. Now you need to keep track of all your queries, all your rays at the same time, which is also costly, which you don't have to do otherwise. And there are some other downsides to this. But yeah, keep this in mind that sometimes maybe you can flip those things around and build your acceleration structure over your query instead. This also leads to something like the, idea of dual hierarchy traversals, where you have two hierarchies and you kind of try to traverse them against each other. This might be something you want to do in collision detection, where you even have the same hierarchy that contains all of your geometry and you start traversing them against each other. Yes? Oh.
Yeah, sorry. So you mentioned building a hierarchy over rays, but that isn't that equivalent to rasterizing and culling those?
That's an interesting question. Let me
because essentially the difference between ray tracing and rasterizing is you have a double loop, and in which order you go through the loop. So the hierarchy is which loop evaluation are you speeding up?
So that's true when you have primary rays, so your primary visibility, where your rays are super coherent, so you have this image that you're looking at. You can do this on more complex rays as well, so instead of having the rays pre-organized, so in this case you actually have this free data structure to begin with, your screen, which is just a grid. If you have random rays, you could still try to build a hierarchy, probably not with bounding volumes, but with cones. That's the one technique that I know. And then you traverse your triangles against this hierarchy of cones, and they can point into very different directions, which is a bit more difficult to achieve with planar rasterization. So planar rasterization, you assume that you have a single origin point, your eye or your camera, and then you have a screen in front of you, and you probably sample it in some sort of more or less regular way. And that would be then the equivalent of your acceleration structure. So you might not even want to build a full BVH over it. There's some work by Intel around Larrabee. That was a while ago, where they tried to, for the nth time, design a GPU. And the way they did rasterization was actually build a subdivision quad tree-like thing. So you could imagine that that's a little bit similar to what you're saying. So you would traverse your triangle against the quad tree that is your screen. But it's an interesting question. So if you have coherent rays, you can do something like this. I want to briefly also show this in a slightly different way. So I talked about binary search. This is kind of equivalent to a binary tree. In fact, it's kind of a nice balanced tree. I'll get back to this in a bit. This is one nice way of storing data structures, like BVHs. First, I want to show this. It doesn't look great. This is still a binary tree. It's just a very poorly built binary tree. it's the same data, it's the same number of nodes. You would traverse it with the same traversal method, but on average you would have worse like performance. So that gets us to my last two observations I want to make here. And one is that we can have different data structures for the same data. And there is some sort of inherent measure to quality of the data structure. So some ways of like representing this or like building this acceleration structure will be better than others. Whereas, yeah, you can definitely make it worse. It's relatively simple in this 1D example, but it gets a lot more complicated once you go to 2D and 3D, and once you have things that aren't points, but like triangles or even more complex objects. And yeah, I mean, I already mentioned this. Sorted array is kind of a binary tree, and well, a compact binary tree. So now I can give you the plan. The main part is going to be about building these acceleration structures, building these bounding volume hierarchies. And I'll outline like two main approaches and go into a little bit more detail in the second one, like the bottom-up or agglomerative build. I then want to talk a little bit more about the representation of these, like how do you actually store these in a reasonable way. I'll point out one specific idea. And well, I also want to talk a little bit about the choices you can make. Like, is a binary tree actually a good choice, or is something else, like a wider fan-out, useful? I'll very briefly talk about traversing things and some things to keep in mind about this. And finally, there's like 2 or 3 slides just discussing more about dynamic data and updates. Yeah, during this, I'll then concretely outline like my go-to method of building a BVH as well. So hopefully you'll be able to walk away knowing roughly what you would have to do if you had to have a BVH by the end of the week. Code it yourself. So let's start with building this stuff. Conceptually, this is relatively easy. Like, we have a bunch of things. We want to create groups of objects that are kind of close together. And I mean, this one possible grouping at the lowest level. I've taken created pairs, put them into nodes. We then combine those next level up in the tree, and finally, in this case, we have a root node. And the structure would be something like this. Root at the top, we have one interior level, and we have the lead nodes, which then contain our data. So back to this. I mean, when I drew this, I made a particular choice. I could have made a different choice. Like, I'll switch back and forth a little bit here, which would have given us a slightly different tree. And it's not super easy to see which one is obviously better here. So that's kind of our first challenge when building these things. Like, finding the optimal BVH is probably intractable. Like, it's an NP-hard problem. And it's even worse that we don't even know what optimal means in this case. Like, what is the best possible BVH? And the answer to that is something ultimately that makes our queries faster. And in fact, our specific queries that we want to do. Or maybe if you're trying to do this in something like a real-time application, actually the best one is the one that makes building and the queries the fastest, rather than just one of them. But neither of those are a very good measure when you're building these things, because you don't know the exact queries you're going to make typically. So you have to have something that you can use during the builds. I mean, one thing that we rely on here are heuristics. For ray tracing, the most common thing is the surface area heuristic. It's been around for a while. I'll try to outline the idea behind it here briefly. Basically, you can show that the probability of hitting a certain child node within a parent node is, it depends on the area of the child node compared to the parent's area. So you use this probability to model the cost of traversing this BVH. So you assign some sort of cost for going down a certain node or intersecting towards certain objects. And then you try to minimize this total cost. Now, this is still a little bit impractical. If you have your tree, you could evaluate this metric quite easily. But during building, we don't actually know what the tree looks like, so we want to instead introduce some estimates for costs of certain subtrees. So some divisions that we make will have an estimate for those splits, and we use the surface area to kind of like calculate the probability of having those things. Now, the surface area heuristic, at least where I come from, is the most common thing you'll see in books. But one thing to keep in mind that this actually kind of assumes ray tracing. So you assume that this is with uniformly distributed long random rays that you shoot through your scene. If you have some other type of query, like let's say a range query or a collision detection, that might not be the right heuristic for you to use. Real-time collision detection, the book by Ericsson, it outlines a few different strategies that are kind of interesting, like minimizing the volumes of the subtrees, minimizing the overlap between different nodes in your tree, or even minimizing the maximum size of a node. And all of these are possibilities. It's not clear which one is best, and it will depend on what you're trying to do. Now, with this out of the way, let's look at some building strategies. I would categorize these kind of into two main ideas. One is building them top-down, and the other one is building them bottom-up, an agglomerative build. Now, the very general statement about these is that doing the bottom-up builds is typically faster, but gives you a lower quality result. You also have some problems with, or you can run into some problems with precision. Top-down builds are more expensive, but typically give you a better tree for whatever measure you have. You're not locked into one of them, so you can definitely build part of your BVH with one of them. So you can mix them, like you could build your top part with a top-down build, and then the subtrees towards the leaf level with a bottom-up build to make it slightly faster. Top-down build is pretty much a classic divide and conquer thing. You start with all of your objects, you split them into two groups, and you recursively repeat this until you have reached kind of a desired level of subdivision. Again, people often go down all the way to one node, one object. I would typically not recommend this. You often want to keep like a few objects, 8, 16, maybe 32 objects at the bottom of your tree. Just to spare me some triangle drawing, I'll actually subdivide this a few times. But yeah, top-down build. We want to somehow split these into two subgroups. Once we've done this, we'll repeat this for each one. And the big question here is, where do we actually split these things? And there's a lot of choices that we have to make, like which axis are we splitting on, assuming we have axis-aligned bounding boxes, and where in this thing do we split. You could now always decide, hey, I'm just going to sort objects around one of the axes that I've chosen, pick the median. This gives you a nice, like balanced-ish tree. But it's likely suboptimal in the end, despite being like theoretically a nice data structure. So one thing that you can do is actually use the surface area heuristic or another heuristic to make these decisions. The way this would work is you consider, well, you evaluate the surface area heuristic for different types of splits, and then basically pick the best one. Then you calculate the actual bounding volume for each subgroup and start repeating it. We can see the challenge here a little bit, that like if you have a lot of objects, there's a lot of potential splits. So one of the one of the core challenges around this is figuring out where do you place your potential splits, and evaluate the surface, or like your heuristic for those things, rather than trying everything. That's typically infeasible if you have really a lot of objects. Now, these types of builds, again, they tend to give you very good quality trees, at least if you have a good heuristic for them. They're more expensive to build. Like even if you have a good choice of potential splits, you still have a lot of SAH evaluations that you have to do. You can end up with very unbalanced trees, and this can be quite tricky to implement in parallel, so on a GPU or with SIMD. I'll move on to the bottom-up build. This is the one that I kind of like prefer. As the name suggests, we kind of flip this upside down. So instead of starting with all objects, we'll start at the leaf level, and we try to find groups of objects in this leaf level, group them together, build a leaf node out of this, and then we do this for all of the objects that we have. Once we've done this, we kind of move up one level. We take our leaf nodes, and we start grouping them together to create like the next level up, and repeat this all the way until we reach a parent node. There is this kind of like magic step here where we want to find probably close items, which is the kind of main challenge. It seems like this is a little bit circular because we want to use maybe a data structure to do this. And there is a core trick to this, which is the Morton curve or set order curve. How many of you have seen this already sometime? Okay, yeah, a few hands. Yeah, this is a space filling curve. We have this kind of like set-like shape that seems to repeat a bit, like here. It's also self-similar, so this set-like shape kind of repeats upwards. So the nodes like are arranged in a larger set, and then if you go up one more level, you kind of have this ordering again, and it will continue all the way up. From this, we can compute something, well, the Morton code, which is basically if you have a 2D or 3D coordinate or 4D for all that matters, you can have any. Well, you can scale this to larger dimensions. You can compute the index on the Morton curve, and this will be your Morton code. The way to do this is to discretize the position. So we have somehow reduced our things to a single point. Like if you have a triangle, you might want to pick the center of it. If you have something more complex, you'll have to figure out a way to kind of pick a representative point for that object and then compute the Morton code for it. Once you have discretized the position, you take like all of the different coordinates and interleave their bits. So in binary, like these are binary digits, this will look like this. We have an x coordinate here, it's 5 bits, a y coordinate, also 5 bits, and we create this 10-bit code where we just take the lowest bit from both, put them together, next higher up, and so on. Same thing works in 3D. You just interleave them a little bit more. And I have one more example here just to show how this is. So if you have x coordinates 9 and 5, those are the binary values from it. We combine them together to create this index along the curve. One key reason why we use this is that this is very efficient and simple to compute. The common implementation that you'll find is something like this. You have a function typically called something like spread bits, and the exact implementation of this will depend whether you want to do it in 2D, 3D, or 4D, or whatever you have, where you take essentially the bits in an integer and you spread them out so that they have like an extra 0 between them, or 2 zeros between them in case of 3D. So if we were to do it like for 1, 0, 0, 1 in 2D, we would get 0, 1, 0, 0, 0, 0, 0, 1. And the same thing for 3D. And you can then combine those for, like you compute it for each axis and combine those to create your Morton code. So here I take the y-axis, I shift it over, so the bits from that axis will go into the zeros of the other axis and vice versa. 3D, same idea, like we shifted over by 2. We had 2 kind of like empty spaces in the x code, and we shift z over 2, y over 1, and so on. You can find a lot of implementations for this. I mean, you can probably type this into your favorite AI, and it might almost give you the right answer. Double check this. But it usually looks something like this, where you kind of like it's, again, a divide and conquer approach where you take your 2 values, you first spread them apart by 8 bits. So you take the top half, shove it over. You take the nibbles and kind of shove them over a little bit, and then you take the pairs of bits, you shove them over a little bit, combine them back, and then finally you do the last step there. If you're not familiar with bit filling hacks, I recommend studying it. It's a great webpage where they talk about all of these things. It's also common enough that we have specialized instructions that can help us do this in a single instruction. So pdep, the bit deposition instruction x86, would let you do this one step in just one go. If your eyes glazed over at all the code, the main takeaway is that this is fairly simple and efficient to compute. Why do we want this? Well, in this grid, we have this special property that values that are close together on this curve are probably also close together in 2D or 3D space, or again, 4D, 5D, and so on, typically. So I marked like 4 points here, and I mean, they're close together in 2D. They're kind of neighbors on this discretized grid. If you count the kind of like steps along the curve, the maximum distance is 9 steps. So like distance between these, you take 9 steps along the curve. We can compare this to the row stride of the grid. So this grid is 16 elements across in this example. So if we just pack this normal like row matrix or column matrix, some points would be at least 16 away, depending on what axis we go along. So this is nice. Like we usually get points close together, although I mean you can probably spot the problem already. This doesn't work always. Again, 4 neighboring points put into kind of a less ideal position here. The furthest distance along the modern code here is very far. I started counting, then gave up, but basically you can see like going from, well, I have a pointer here, from here to here would mean you go through all of this stuff here, this quadrant here, until you end up over here. So that's a lot longer than with just normal row matrix or column matrix packing. That is kind of our main problem with this thing. It's something that will cause us grief once we start using this a bit, so we need to be aware of it. So now I'll outline how we use this, how we do this bottom-up approach. So we have some sort of objects. We figure out their like representative point position. We discretize this position. Now, common thing that you will see people do is in 3D, you will discretize it to 10 bits each, because you can then combine these nicely into a 32-bit integer with 2 bits left over, but fine. So you get a 30-bit modern code. For each of the discretized points, you do compute the modern code, and then you take the objects and sort them by this modern code. And now you can start grouping them together along the line along this sorted order. I have some illustrations here. I have a pile of triangles. We would, as mentioned, figure out some sort of representative point for these, marked here in white. Discretize it and figure out where on the Morton curve they are. So, for instance, this point here, it would be probably index, well, 3, 0, 1, 2, 3. This one is a bit further down, and so on. I would now take these triangles, sort them by the Morton code, giving me this order here. So, first, second, third, fourth. Just follow this curve, and they will appear in this order. And now we can start grouping them together. So, if we just take 2 objects, first 2 objects here, thanks to the Morton curve, their chances are that they will be close together in 2D space as well. Next 2, same thing happens here. And, well, okay, this wasn't as great. So this is one of the problems we discussed, that, well, they are close together on the curve, but actually far apart in space. We have 1 left over, so we'll have to create a node again. Now we have our leaf nodes. So now we can start building the other levels for this. So we take these nodes, 2 of them in this case, combine them together to create a node, second one as well. That will be our interior level in this case. So we're now 1 step up. And finally, we do this again. This creates our root node that contains all of the objects where we start our queries. Yeah. So what I presented here is a simplified version of this LBVH method. You've seen it up here in the slides, the linear BVH that was presented in a paper called False BVH Construction on GPUs. It kind of jump-started a lot of doing this in really fast back in 2009. The main difference with the full version is that we try to avoid kind of these cases here. So what I did is just really a greedy build where I grab these objects, I put them together. This is really easy to implement, really quick. But yeah, you end up with some bad things here. What their method does is it looks at kind of like the Morton code for the different triangles. It tracks common prefixes, and the common prefix length lets us see whenever there is kind of a large jump. And that tells us a little bit whether or not we should combine like this node forward with this one, or this one backwards with this one, or if it's better to go somewhere else. So probably here we will want to combine, but these two we wouldn't want to combine. One thing that we lose with this is if you do it just greedily, you get a nice complete like tree with the same numbers of elements in each of your leaves. That probably makes your code a little bit simpler. If you avoid like putting these two together, you would have probably a node with one triangle, then another node with one triangle. Chances are you wouldn't even want to merge these because there's also this large, there's a large distance between the two. So you would end up with more nodes in your tree, although they would be smaller. Now, this simple greedy bottom-up method that I just described, like this is basically my first attempt at whenever I have to do this. It's relatively simple, and you get some nice properties for later on. So, as mentioned, you can determine like your leaf node size, your node size in general. Like you can pick it to be 2 or 4 or 8 or whatever very easily. You get a complete tree. Which can be good or bad. I'll talk a little bit more about this when we talk about the representations. But it makes it very easy to like implement, move things around. This is also relatively easy to implement on the GPU if you need to do it. The only non-trivial thing that you need is a nice sorting function. Like typically what people would use is a radix sort here. Radix sorts are relatively easy to implement, although obviously you can also find implementations for this. And yeah, it's easy to tweak a lot. If you've then determined that, hey, or well, I would then maybe see if this works, if it does anything useful at all. It's also easy to kind of improve on this. So one thing that you can always do is then go more towards the proper LBVH method, so avoiding these jumps and seeing if that actually helps like improve the quality of the tree and make your queries faster. There's a lot of different techniques to optimize these builds as well. So you can look at like subtrees afterwards, after you've built it, start switching things up, splitting nodes, merging nodes, changing the order in which they appear and so on, to improve the quality of the tree a little bit. And finally, this is something that the physically-based rendering book does, physics-based ray tracing book does, is it actually then mixes builds. So it builds an upper level with the top-down build, a bit slower, but it gives you a nice start of the tree, and you can keep this agglomerative bottom-up build for the lower parts. Those are very fast to build. And this also helps you a little bit with the precision. So remember, when we did this, we only have 10 bits. Well, in 3D, 10 bits, or maybe 20 bits for 21 bits. If you go to 60-bit key. So you have limited precision here. So doing this on smaller volumes is also good. Cool. I want to now talk a little bit more about the BVH representation. So hopefully now we have an idea of how to build these things. How do we actually store them in memory? So what do we do when we combine these things into nodes? What do we store? The key considerations here are, well, memory usage, although probably more memory bandwidth and how much memory we have to read. Also goes hand in hand with like caching and memory access patterns. So if you jump around a lot in memory, we will cause a lot more, memory to be read and transferred. And so, and also how well we can then parallelize, let's say, our queries. How can we use like SIMD, or how do we traverse this on a GPU? Now, with respect to the first one, I want to briefly go back to this scene here, just to give you an idea of what kind of values you would have. So, again, this is 5.7 billion instance triangles, and the resulting BVH structure, like the acceleration structure, is 275 megabytes. It's, I would say, significant, but not enormous. Although you can also imagine this is probably a fairly compact BVH, like a lot of engineering effort has gone into this. I was talking to some engineers at NVIDIA who work on this stuff, and one common request that they get is like, hey, can you tell us what your BVH looks like? Can you tell us the memory layout so we can play around with it? And his response was, well, you have an entire team of talented engineers working on this. It's unlikely you will beat them, but I think the common answer back to that is, challenge accepted. I mean, might fail, but it would be good to try. Well, I'll mention the structure here a little bit later. Now, I asked Thomas, my PhD student, for these numbers, and what he discovered while looking at this is very recently another extension, Vulkan, appeared that lets you compact these structures further. So by default, you get something that would be 275 megabytes, at least on the version of drivers and graphics hardware that he tested on. But you can then ask the driver subsystem to compact this further and shrink the size to 105 megabytes, although the processing cost for this is not insignificant if you do it for the whole scene. But yeah, I mean, storing things efficiently is a concern. 275 megabytes is enough of a budget on consumer hardware that you want to keep track of it. So let's talk a little bit about storing trees. And one of the things I want to go back to is this idea of like storing things in an array. So I'll start with talking about the pointerless storage method, and then briefly just talk about things with pointers and what I tend to do when I have to do this. I mean, pointerless is nice if you can do it. I showed this earlier with the binary search, that our binary search is kind of equivalent to a binary tree in a sense. So if you have a sorted array, we can kind of implicitly imagine that there is a tree on top of it. Like we start in the middle, we have the two sides, two children, halfway on each side, and so on all the way until we reach the data. Now, we can improve things a little bit on this idea, generalize it a bit, by rearranging our sorted data to kind of store it in a breadth-first order of this tree. So in this case, we would start with the root node, store it first, and then traverse down, well, in breadth-first order, so 3, 8, then we go through the next level, and finally we append the data here. And I mean, this is what you would call an implicit tree, assuming quite a few will have already seen this. But just make sure everybody's caught up on this. We can now traverse this tree with just some simple rules. So whenever we want to descend, we can take the index of an element and multiply it by 2. And this really hurts me that I have to start with 1 here rather than 0. But yeah, if you start here, and want to go to one of its children, we multiply by 2, so we have 2, or add 1 if you want to go to the other child, 2 or 3. And similarly, if you want to ascend from somewhere, we just divide it by 2. I have an example here where, well, it just walk through it again. We want to traverse down to 7 here, so we start at the root. In this case, we will go to the right child. I have an extra step in here. So if you want to go to the left child, we just double this. I already mentioned this. But if you want to go to the right child, well, we'll double it and add 1, so we end up at 8. Now we want to go to the left child, so we just take 3 and double it to 6, read the element there. We're now here. And if we now want to go to the right child again to actually find the element in our array, we would double 6 and add 1, so we should go to 13. Now, this is nice. We didn't have to store any pointers in this, but it has a few disadvantages. So it does require a complete tree, which means if you have an uneven amount of elements, like this is very nice. This was 8 elements here. If I had one more element over here, you can see that it would kind of require another root node and add a whole thing over here. So you might need some padding to do this, or that's at least the easiest way. There is a cool paper, 2020 Eurographics, where they describe a method to not have to invest the memory. You basically trade memory for some extra computations, so that you can have a more or less implicit tree without storing this part here, with just a little bit of extra metadata. But that's one of the kind of disadvantages of this. The other thing is that it tends to be a little bit more difficult to update and restructure once you have it. But the nice thing is it's compact. One thing that makes it compact, you don't have to store any pointers. And you get quite a bit of like locality in memory in different places. So, I mean, one thing that maybe doesn't matter too much is up here when you start your tree, like those are close together. But also when you're like down here, if you're like searching for a certain element in a subtree during ray tracing or intersection tests, you tend to go up and down a lot on these lower levels, and they tend to be then relatively close together, so you can get some caching and stuff out of this as well. Yeah. Now, sometimes doing this pointless is not possible, or it just is easier to deal with the pointers. So here are some considerations, like one case where this might be necessary is if you don't have a pure tree, but you actually have a directed graph. You can't put it into that data structure. Another thing is if you have like more subtree-based things where you have different subtrees that you link together, you will have pointers. What I would suggest here is, I mean, don't do the thing every tutorial tells you where you malloc individual nodes and stuff. That's not a good idea. You can always place things in a compact array. So allocate an array, use an atomic ink or whatever to allocate elements out of it, and then place things in that compact array. That also lets you use smaller indices. Like this. So some people, when I say this, will probably put up their hand and say, like, no, actually I work on exabyte data. But for a lot of us, 32-bit indices are quite a lot. Like you get 4 giga elements of stuff. One element is probably more than 1 byte. So on normal machines, at least, we tend to fill up our memory with that. So you don't need full 64-bit pointers. You can use something smaller, 32-bit, 16-bit, whatever you can do. Yeah. It's also then much easier to kind of manage. So if you have this data structure both on your CPU and GPU, you can just take this array and copy it over. Because it's based on indices, you don't need to update like pointers or anything. They are just valid wherever you put this thing. You have the base address and so on. So it's also easy to like move it from CPU to GPU or vice versa and so on. Plus, you get, again, a little bit of locality back. Like things are in your array. Chances are, if you allocate them carefully, things that occur close together will be like close together. So you have a chance at getting some like caching out of this again. There are, of course, downsides of this as well. I mean, pointers add storage. Pointerless trees don't have pointers. But on the other hand, this might not be as much of an effect. We're already jumping through memory quite a lot, regardless of which method we have. So our caches might not be that useful regardless. So it's worth, well, I mean, it's worth not discarding a pointer-based tree entirely just because it adds this little thing. We actually had this observation very early on where the examples that I had were binary trees. This is another suggestion that I would, well, tell you to consider if you're building this. We tend to illustrate binary trees a lot, but they are not the only option. You can definitely make different fan-outs, so have more child nodes per thing. Convenient numbers might be something like 4, 8, or 32. AVX on the CPU, AVX2. 32 is the common subgroup size on GPUs, so if you have a warp or subgroup that you traverse, 32 might be a good choice. Cool thing with the bottom-up build is that you can very easily change this, right? You can just build larger nodes at each step. So instead of combining 2 things together into a node, you now grab 4 things. Next level up, you grab 4 leaf nodes, put them together into a node, and so on. The illustration here just is on the leaf level, but you can do this separately for leaves and interior nodes. And that's also something to consider, that if your tests for individual elements are quite cheap, having nodes with more leaves might also be useful. You can have 64 triangles in your leaf nodes. Checking those might be very cheap if you do some sort of intersection test, rather than having each one in an individual leaf node. But then you can make the top of your tree have a different fan-out. Doing things with a wider BVH, a larger fan-out, has, I mean, it's a trade-off, but it has some nice advantages. So one of the core advantages that I've seen is that it makes your hierarchy a lot shallower. And one example that I have here is with the 32-bit fan-out, 32 fan-out, so each node has 32 children. If you just go 4 levels, you will have a tree that covers up to 1 million elements. That means whenever you go searching for something, you can do fewer levels of recursion in your tree, although you maybe have to then do more tests at each level. I like this because it lets me do some lazy SIMD tricks. So, for instance, if I were to traverse this on a GPU, I could take one subgroup, so one group of 32 threads, and assign them to one query. Now, inside of this query, I just test all of these 32 elements in parallel, figure out which ones I need to traverse, remember that, and then take the whole group and traverse down to those in turn. Yeah, and similar things you could do for CPU-based. So like 4 might be convenient if you have AVX, although most of us will have AVX2 on our CPUs, so you could do this with 8. And especially in AVX, where you don't have like this scalar approach to programming with individual threads, I found this like a very easy way to at least get some advantages of SIMD in queries if you implement this yourself. Yeah. This also works with pointerless trees. Like instead of multiplying by 2 and adding 0 or 1, you multiply by, I mean, here I have the example with 32. And you then add between 0 and 31, depending on which child you will go in. So this also just kind of works. I've used this a few times. One time it saved my butt a bit by giving me the 10x speedup that I needed. So if you want to have 1 million elements and you know that like that's the upper bound, you only need 4 steps of recursion. That means you can now unroll this complete like recursion or loop that you have to check the different levels and just kind of have it as a straight line program almost. On a GPU, this gives you one large advantage, which is you don't need to do any dynamic indexing into an array. So that means you don't have to store like your stack data in VRAM. You can keep it in registers, or at least part of it in registers, which is much, much faster. So my advice around this would be, if you have to make a choice, try going pointerless. These are super easy to build. Like you sort, you reduce your tree levels. They're easy to move around, so you can build them on the CPU, put them on the GPU, vice versa. Not sure why you would do that, but in theory. If you have fewish queries, I would definitely suggest trying larger fan-outs. If you're on the GPU, fewish might mean like 10,000, 20,000, 30,000 queries. 32 would match your subgroup size. That's fairly standard across all of the GPU platforms at this point. So that's a decent choice. You could even go 64 if you're targeting some older AMD stuff. However, if you really have a lot of queries, so if you do ray tracing, you have millions, hundreds of millions of queries, it's probably better to go with the standard approach where you don't have this large fan out and you just pick one thread handling one query and then traverse the tree that way. CPU, kind of the same deal, honestly. If you're handwriting SIMD code, larger fan out is nice, so 4 or 8 or maybe 16. Makes writing the SIMD code quite neat and compact. If you are able to write like the shader-like code where you focus on like a scalar function that just then happens to execute in a SIMD environment, so something like ISPC, you can try the other approach, especially if you have a lot of queries again. So with this, let's briefly just highlight some things around traversing these things as well. Second to last part. Now, first thought typically tends to be something like this. Hey, this is just a tree. Let's just write a recursive function, traverse it. Yeah, this is a common source of disappointment when people do it. First off, if you're actually writing this on the GPU, maybe in a shader, they might not let you do any recursion as a language feature. CUDA lets you do recursion. Don't do recursion in CUDA. It's typically a bad idea. It's very expensive. You generate a lot of memory traffic. You lose a lot of control. You're really at the mercy of the compiler. So what you usually want to do is you want to kind of create your own stack. Minimize the data you put on the stack, minimize the way you access it. Sometimes it's even worth caching some values in local variables for like the bottom part of the tree, just to minimize memory traffic. If you do this, remember on the GPU, this will require dynamic indexing, where you compute an index, you random access memory. So this thing has to kind of live in a more expensive memory space like VRAM. Local memory is also VRAM, not registers. And try to minimize stack size. Again, keep in mind that a tree depth of 20 or 30 gets you quite far in numbers of elements. So if you're aware of like kind of what size of data you have, or even can propagate this into your shaders, that's really useful. One nice thing that you can try doing, tends to be my first go-to thing, is instead of having a stack like normal with pointers and stuff, you model the stack as a bit stack. So for each element, we have 2 childs that we can test. We do the tests and we remember whether or not we have to go to the second child and put that on our stack. That means in a single like 32-bit integer, we can store up to 32 levels in our stack. We would then traverse the first child, we remember the second child. And at some point when we get back to this, well, we'll go up this bit stack and check whether or not we had to take the other branch. There are some extra things that you need to remember, like your current level, a pointer to the node for these things, but it really lets you go like ascend very quickly. You can like do these bit counting tricks to know how far up you have to go until you have to check a second tree. So like count R0 CL set, like count leading zeros or find first set, those kind of intrinsics that you have. core takeaway, like think about these things. There are quite a few papers around this, like the stackless traversals, the restart trails, and so on, that tell you how to do this more things, like more efficiently. Core thing is minimize the amount of data you put on the stack. Finally, a little bit more about updating BVHs. So far, we've just talked about generating these things. Often we will have dynamic data. That's really the interesting case. Like you have animated meshes. If you have a simulation, things will move around, etc., etc. Whenever things change, you kind of need to update your BVH to match your changes if you want to do queries against it. So you have two choices, rebuild from scratch, the way we've discussed, or refit things to match this new data. I'll just outline the second one first. It's relatively simple. Like we start at the leaves. We check if the elements have changed. If so, we change our own bounding node to update this, and then we basically propagate this change through the tree. I've illustrated this here with one of the earlier examples. So we originally had this node here. Two elements here, one element moves around. So first we check these leaf nodes. We see that this one has expanded. We need to grow it to now include the moved element. And then we expand the nodes to match this. This is relatively cheap. Like you just do a single pass over each level. You propagate these changes upward. The problem is that this causes your BVH to degrade over time. These nodes become larger, and maybe at some point, like the grouping would change. Like this moves close to another triangle that was somewhere else, and in theory, we should build now a node over those two rather than over these two. That's tricky to do in this context, so you would have to do some extra work. So if you do this for too long, your interior nodes will get very large. You will get less and less benefit from your BVH. There's a couple of pragmatic solutions to this. If you need to do this, one is, you just refit for a while, especially if you have smooth simulations, the changes won't be that much. The degradation will be small. But after a while, when you either detect that the errors become too large, or you just have a regular interval at which you want to rebuild, you scrap the whole thing and start from scratch and rebuild it. Just rebuild it. One thing to consider is also keep your dynamic data separate from your static data. Static data doesn't change, so you don't need to update it, you don't need to rebuild it. So if you know that you have some dynamic stuff and some static stuff, like try to separate them, keep them apart. And this is something that RTX, like our hardware ray tracing, does. How many of you have tried programming hardware ray tracing stuff? Few hands. Okay, cool. If you look at this, one of the things that you will see very early is that you have two different types of acceleration structures. You have the bottom level acceleration structure, top level acceleration structure. The bottom level, in very short, the bottom level acceleration structure would be the thing that actually contains your different objects, triangles typically, for this kind of stuff. But yeah, whatever is in your leaf node, leaf data. You build a number of bottom-level acceleration structures, maybe one for each object, and then you combine them into these top-level acceleration structures, which kind of is the root of your tree. The reason why we do this, it's then your scene, is you can build bottom-level acceleration structures for your static objects and keep them around for a long time. You probably want them to have a better, more expensive build, whereas for your dynamic objects, well, you keep them in a separate bottom-level acceleration structure that you have to update and rebuild frequently, maybe cheaper build. But then each frame or each simulation step, you regenerate the top-level acceleration structure that combines them. And this is, at least in these APIs, made to be cheapish. So, yeah, you can do this more frequently. And that just minimizes the amount of rebuilding and refitting you have to do. I showed this image already with the timings, and you can get an idea of like the different costs. So building the bottom level acceleration structures for this scene, it's instanced, so it's only for these 4.6 million unique triangles, took, in this test case, 43 milliseconds, which is a significant chunk of time if you're trying to do real-time stuff. Whereas combining everything in the scene, like for all of these 5.7 billion instances triangles, took 9 milliseconds. So this is something you can do more frequently. Okay, I wouldn't want to do 9 milliseconds each frame either, but yeah. Now, I tend to go for an even more pragmatic approach, at least first time around, which is you just rebuild things and hope that it's cheap enough. Like this has been the case, especially if you do the very simple, like greedy agglomerative bottom-up builds. Millions of objects, 10 million objects, fine. It takes you a couple of milliseconds. It's done. The nice thing about this is you don't have to worry about differences in performance. It's almost, it kind of stays at the same cost. You don't have to worry about like, will all of my dynamic rebuilds happen in a certain frame and I get a spike there, or like try to spread it out. You just always get the same cost. Okay, I'm getting to the end of the presentation. So I'll collect some thoughts and let's see if there are any questions afterwards. So one of the core things I wanted to highlight here is, unfortunately, we don't really get our data in pre-made nice acceleration structures and BVHs. So we need to build things, and that's really the core challenge about using these things. We need a nice build that is cheap and gives us a good enough quality tree. And this is especially important when you have dynamic data that changes often. When we choose these builds, we can choose trade-offs. So we have faster builds, which give us worse BVHs, but we also have slower builds, which give us better BVHs. And it's not always clear which one you want to do, because ultimately what you want to minimize is the total time spent on building and querying. So if you have fewer queries, doing a worse build might be worth it because you save time on the build, and then you don't need, well, you don't do as much querying. Whereas if you have a lot of queries, you probably want to have a higher quality data structure because that will save you time more on the queries rather than, well, you spend it on the building instead. What exactly like defines a good BVH will really depend on your use case. So it depends on what kind of queries you do. Like, is it ray tracing? Is it range queries? Is it collision detection? And you want to make sure that you kind of pick a build or like a measure that matches this use case. You can sometimes even go further and specifically look at the queries that you are going to do. We had an example for this with the question as well, like if you know that your queries are raised that are coherent, a different type of acceleration structure might be even better than a generic BVH. Although, again, I would say if you want to start something you're not sure, start with a BVH. I try to outline a few methods, well, give you an introduction, an overview of how to build these things, and then specifically focused on this bottom-up kind of build style with a bit more detail. My hope is that you can kind of now go and implement it, maybe even without Claude assistance, although it will do a reasonable job. If you really want to do it simple, quick, just sort, well, I mean, discretize, Morton code, sort, combine things greedily, and you have your first BVH with a relatively fast build. I discussed a little bit about the different representations, so my suggestion there is don't do the like tutorial thing where you, again, malloc objects. Think a little bit about how you represent this data and how we can minimize or like make them more compact, minimize memory traffics, and so on. And this is really where like paying some attention is useful. This is where you get your like 2x or 10x over just doing a basic BVH already. Yeah. This is kind of obvious. You can do this in 3D. You can do this in higher dimensions. So we've applied this to 4D and 5D data in some cases as well. We've tried to do this with cones. So you have a position, your origin of a cone, but also a direction. That would be what you need to build, let's say, array hierarchy. This gives you a reasonable starting point. On that specific example, I would say you have to be a bit careful about the angle. Like things will spread out very quickly in terms of angular. Like you get large cones, which means you cover a lot of space very quickly. But again, you can try doing it. Probably at some point this stops scaling. Like if you go to super high dimensions, first off, like if you try to do the bottom-up build, you will run out of bits in your modern code. But also, like the BVH becomes progressively worse and worse for high-dimensional spaces. So probably there you want to do something else. KD trees are a choice. The final thing I want to say is also, yeah, pay attention to your queries. Know, again, like what you're doing. And one thing I've seen a few times also happen is that people end up doing queries that kind of retrieve a lot of data. So imagine you have a range query that covers 90% of your data. Maybe doing a BVH at that point just adds a lot of overhead because you end up doing a lot of traversals to pick out those elements without getting that much benefit because you just get basically everything back anyway. Okay. That's it from me. I think we have a lot of time for questions. I have one last thing I've been asked to mention. At Leeds, we're trying to, well, we will be looking at hiring somebody. I don't know what the proportion of PhD students and people who are actually looking for this kind of stuff is, but maybe this is also just an encouragement. Like, despite what you hear out of Meta and so on, where everybody's getting fired, well, there are still jobs out there. Thank you. I don't think they're kicking us out right now. So are there any questions, or is everybody just ready to jump into the river and cool down?
Yeah, nice presentations. Because you did it bottom up. So yeah, thank you for the nice bottom-up presentation. Any thoughts about existing solutions? Intel Embry,
Yes.
Seagull, probably lots of other libraries.
Yes.
So what exists? What would you do, recommend, not use?
I mean, if you want to do ray tracing, Embry by Intel is a good choice for doing CPU stuff. Obviously, you have hardware ray tracing now, so optics, again, for ray tracing. You can also use Vulkan or Direct3D with the RTX style of ray tracing. You kind of don't have to worry about a lot of things, but you also have to then just do the things that they do. So one observation with that is that, like, doing hardware ray tracing gets you very much back to a fixed function pipeline where it's really designed to do ray queries and not much else. So if you want to do ray queries, great. If you don't want to do ray queries, you have to hack something on top. I've seen some papers try to do this. So recently at i3D, there was a paper about doing 3D Gaussian splats with ray tracing, and you kind of like try to cleverly hack this on top so that you can use the ray query to return a set of things. People have tried finding like range queries where you bend your objects and so on. My personal opinion, like, I mean, try it if you like. Try something like this. I would say probably most of the time you will get better results if you like have a very different style of query, trying it to do yourself. Yeah.
Okay, thank you.
You already mentioned some other sort of representations like Gaussian splats that are also, these methods are used, and in the illustrations it's mostly triangles. Are there any other sort of representations or data that you are familiar with that uses these types of structures in applications?
I mean, surprisingly, like points are useful. Like, I mean, whether it's point clouds or particles in a fluid or whatever you have as a simulation, you can do this.
Like implicits, is that at all? Is that interesting or not?
A little bit in the same like problem that the Gaussian splats will have, where you have to set some sort of boundary. You have to decide where to cut off. Like we had a similar problem with light sources, where how far does light reach? Well, it has a 1/r² fall off, so technically everywhere. So what kind of like, how do you bound this in order to create the bounding volume hierarchy? So if you can find a nice bound, yeah, you can put it into a box and then it will work. If you don't have a very well-defined bound or it's super expensive to find, yeah.
Okay. Thank you.
Then I think there are no more questions. If you have more questions, you can always ask Markus.
Yeah, I'll stick around for a bit.